To understand a lot of the science that we'll be covering in this course, you need to have a good solid grasp on some really fundamental physics and chemistry. In particular, I want to make sure that you understand some very basic things about matter and energy. The most basic building block of matter that we'll be dealing with in this class is the atom. Yes, it's true that atoms are made of even smaller pieces, but tinkering around with those parts isn't something that we need to worry about too much in nature. So it's safe for you to think about atoms as these fundamental, tiny pieces of stuff. This is the representation of what the flavors of atoms look like on the inside, but what we're going to think of them as is just basically these units, okay? These are the different flavors. Here, for example, is hydrogen, carbon, nitrogen, and oxygen. And for our purposes, they never change from one to another. A carbon atom never becomes a hydrogen atom, or a nitrogen atom, or an oxygen atom. Another thing that is true about atoms, at least for the purposes of this course, is that they are never created or destroyed. They never vanish, they never get used up, and new ones don't pop into existence. Finally, one thing you should know is that the different flavors, which are called elements, behave differently. You can't substitute one flavor for another. They all have their own characteristics. You can almost think of them as different roles that they play in chemical compounds. The only time that we'll be thinking about what atoms are made of is when we think about ions. Electrons, which are these little tiny gold balls here, are particles within an atom that have a negative electrical charge. If an atom gets too many electrons, so what's shown down here, it becomes negatively charged and it's called a negative ion. An atom which loses an electron becomes positively charged, and that's a positive ion. Negative ions are attracted to positive ions and vice versa. They'll stick together. Ions with the same charge, like two ions with positive charges, will push one another away. Sometimes atoms hang out alone, but more often they hang out in teams called molecules. In a molecule, the atoms are physically connected to one another, and a molecule can do totally different things than the atoms that it's made of. For example, a hydrogen ion, a charged hydrogen atom by itself, is what makes acid acidic. If you put two hydrogens together, you get this gas that's lighter than air and catches on fire. If you put two hydrogen atoms together with an oxygen, it becomes water. These are three completely different substances, even though they all have hydrogen atoms in them. The atoms in the molecule never go away. For example, when your body burns calories, what's happening is you're taking a molecule of glucose. One of your cells is taking a molecule of glucose, and it's combining it with a handful of oxygen molecules. This sugar molecule, glucose is a sugar, this sugar molecule breaks apart, and the teams that these carbon atoms are in become completely different. All of these atoms in this group over here shuffle around and become part of different teams. You end up with carbon dioxide, which is a gas, and water. But notice what's happened to the atoms in these molecules. You started out with 6 carbons, 12 hydrogens, and 18 oxygens. You end up with 6 carbons, 18 oxygens, and 12 hydrogens. It's exactly the same. It has to be. Getting atoms to move from one molecule to another can be really easy, or it can be very difficult. It's very hard to make some conversions from one type of molecule to another, and they're caused by different mechanisms. So for example, when iron rusts, that's a chemical change. What's happening is that the iron atoms are combining with oxygen. And this is accelerated by certain things like the presence of water. The presence of water is one of these things that causes metal to rust more rapidly. That happens spontaneously, but there are some chemical reactions that don't happen without a lot of help. And often this help comes from an enzyme, a protein, that is inside a living thing. For example, photosynthesis, which is performed by green plants and some other living things, takes place only inside live cells. It takes carbon dioxide out of the air and it puts those atoms together into sugar molecules. Okay, there are some elements that are very common in non-living stuff. Air is mostly nitrogen, that's the blue atom here. There is carbon dioxide in the air, the black carbon and the red oxygen. And there's also a variety of compounds containing hydrogen that are floating around. Water, of course, is oxygen and hydrogen. And in the earth, there are things like carbon, there's oxygen, but this is not a white atom, this is a gray atom, that's silicon. That's very, very common in the Earth's crust. The atoms that are common in living things are carbon, hydrogen, oxygen, nitrogen, and this one's new, this one is phosphorus. Phosphorus is not very common in the non-living environment, but it's very important for living things. And that turns out to be very interesting in terms of the function of ecosystems. We'll talk about that some later. I'm not going to talk about the various kinds of molecules that make up living organisms, but you should know them. They're on page 29 of your textbook.